All right, so our last section we're going to look at for graphing sine and cosine deals with what's called a period change. All right, so we've done the shifting left and right, shifting up and down. We've done the stretching up and down. The last thing we're going to look at is stretching horizontally. Okay, and that would look something like, if I can do it, okay, that would be compressing, and that would be stretching. Okay, so we can do both. What's the normal period for sine and cosine? We called it a period. I said in some fields like electrical, you might use the term cycles per second or cycle. But how many degrees do you have to go through before it repeats itself? Yeah? 360. Okay. Now, that's assuming that you don't stretch or compress it horizontally. Okay? But the normal period is 360 degrees. Okay. And we're just going to start out right away with what the equation looks like. And I'm using the same letter your textbook does. They use this letter. It kind of looks like a W. It's a Greek letter, omega. But the point is, if you put something in front of the x, okay, and you multiply, that's what a period change looks like. Okay, and it can be sine or cosine. The only difference is what table that you start with that I gave you back on Monday. Okay, these are all examples of period changes. The 4x and the 2x one, these are both going to do something similar. The 1/2 x is going to do something a little different. They're all period changes, but remember, you can stretch or you can compress. What do you think the 4 would do? Do you think that would take the graph of sine and stretch it out 4 times as much, or compress it 4 times as much? Trevor?
Compress.
You think it's going to compress? All right. Anyone else? Anyone else think it's going to do anything different? Think it's going to stretch? Well, yeah, it's going to do one of those two. So let's take a look. So here's your original. Okay, just a basic function. Okay, now I'm going to put in a 4. Okay, so I'll graph in red. This is sine 4x. So what happened? Did it stretch or compress?
Compress.
It compressed. Okay, compressed together. So this kind of does the opposite of what you would expect. Okay, you might think bigger number is going to make it bigger, stretch it bigger. Nope. Okay, this is kind of like the phase shift. You've got to do the opposite. A bigger number is going to compress it smaller. In fact, the bigger the number, the smaller and more compressed it gets. Okay, if I graph 8x, okay, compared to the one I just showed you, this is going to be compressed even more. It might be hard to tell because it's just compressed so much. But okay, so what's happening is, for every 1 cycle in the original, you're getting 8 cycles in the one in red now. It's going up and down 8 times. Okay, it's kind of hard to see it, but it is. All right, 2x wouldn't compress it as much. Okay, it would compress it a little bit. But how about 1/2 x? What do you think that would do? Yeah, that's going to stretch it out. Okay, so if I type in 0.5 is the same as a half. Okay, there's the original. And there's 0.5. Okay, that one's been stretched. Okay, so numbers that are fractions, 1/2, 1/3, 2/3, things like that, fractions are going to cause it to stretch. Numbers bigger than 1 cause it to compress. And the bigger the number, the more it compresses. Okay, so we said that earlier. That's what a period change is. Stretches and compresses along the x-axis. Okay, and that's summarizing what I just said. If the number in front of x is bigger than 1, it's going to compress. If the number in front of x is between 0 and 1, it's going to stretch. For this particular section, we'll never deal with negatives, because if you had a negative, that would also cause a flip, just like it did with the amplitude change. But we're not going to deal with that. Okay, so what I want to do for a second is just play what it sounds like when we do this transformation. What happened when we stretched up and down? Like if you had a sound like this, and then you played a sound like that. What would be the difference between those two sounds? The volume. Yeah. If you stretch it up and down, you're making it louder or softer. So stretching things horizontally isn't going to make it louder or softer. What else can we change about a sound? Yeah. The pitch. Okay. So stretching and compressing horizontally, we start to change the pitch. Okay. And the way the pitch is measured is in hertz. Okay. How many times is the sound oscillating per second? Okay. So in this case, it's 998 times. Okay, the one I'm about to play. Okay, as we start to compress that, and my board's not quite lined up. Okay, but now I've compressed that, right? And now I've got a frequency of about a little over 4,000 hertz. Okay, so how do you think that's going to sound? Is it going to be higher pitch or lower pitch? Trevor?
Higher.
Yeah, it's going to be a lot higher pitch. So it's much higher, but certainly nowhere near the upper limit of what we can hear. So if I play that one, this is a sound up around 12,000 hertz. Okay, so getting higher. And then eventually, if I go high enough, just going to turn it down a little bit. Okay, that's playing, but probably most people can't hear that now. Anybody hear it?
You turn it up.
It's pretty loud. I mean, that vibrating sound, that's not the sound. That's my speaker ready to probably explode. But the sound is playing. If you could hear it, it would be very, very high pitched. If I back it down a little bit, you will probably hear this. How many people heard that one? Yeah. Some people still didn't quite hear it. At some point, there's a range where you don't hear it anymore. Okay, so that's high pitched sounds, and humans can generally hear to about 20,000 hertz. Other animals can hear, or creatures can hear much higher pitched sounds than that. Like dogs can hear a little bit higher. I forget the other, I think bats might be able to hear frequencies in the 6 figures. So that's hundreds of thousands of hertz. So much, much higher than what I can play. And then, kind of going the other way, if we play a frequency like that, I can turn it down because it doesn't have to be very loud at all to hear that. Lower pitch sounds, they tend to be easier to hear, or eventually you could feel them. That one's a little hard to hear because it's so low that it would be more of a vibration if you could feel it. But as I start to turn it up a little bit, I think now you can hear it, I think. Okay? So lower pitch sounds, if you play them loud enough, they permeate through objects and buildings and walls pretty well. But if you were to play a high-pitched sound and go stand in the hallway, high-pitched frequencies don't travel through walls very well. So that really high-pitched sound, probably in the hallway, nobody could hear it. But a low-pitched sound, people could if it was loud enough. Okay? So that's what stretching and compressing a sound wave does, changes the pitch. And if we have time later, I'll try to show you a couple different things I can do with generating the exact frequencies that I need to generate to do certain things with a cell phone. All right, so one thing I can ask you, kind of like I did with amplitude change, is a non-graphing question. Okay? So with amplitude change, I can give you an equation like that and just say what's the amplitude. We don't have to graph it. Well, I can do the same kind of thing with a period change problem, except instead of asking you what the amplitude is, I can say, what is the period? Okay, the period is normally 2 pi, or 360 degrees. But if you put a number in front of x, the period is going to change. What does it change to? You just follow this formula. T stands for the new period. Okay, the book uses T, that's why I use T. And to calculate the new period, you take the original period, which is 2 pi, and you divide by the number in front of x. Okay, so we'll start with this one. I want to find the period of sine 2x. Okay, so in this case, I want to start out with just finding the Greek letter in the bottom. Okay, that's omega. In this equation, what number is taking the place of omega? Emma? 2. Okay, so 2 is not the period. 2 is just what goes in the bottom of the fraction to find the period. What goes in the top? Jamel? 2 pi. So a lot of people on the test, they make the mistake of writing the period as 2. 2 is just what goes in the bottom. Okay, so.
At this time, instructor.
Okay, so we've got 2 pi divided by 2, and if you can reduce it, just try to reduce it as much as you can. So Michael, what does that reduce to? Pi. So compared to the original, did the period here get shorter or did it get longer? It got shorter. Okay? The normal period is 2 pi. This period is pi. So this represents compressing the graph. All right, let's try cosine 5x. Hey, Marcos, what would be my fraction to set up the period here? Well, what's the formula we use? What always goes in the top? 2 pi. So 2 pi goes in the top. What's going to go in the bottom? So in the bottom you put omega, which is 5. Okay, that one doesn't reduce. Okay, 2 pi over 5, we just leave it as 2 pi over 5. You don't have to change that to a decimal. You don't do anything else with it. That's it. Okay, so what this number tells you is if you were making a graph and your graph started at 0, this number is where it ends. That is the length of one period. So this graph would end at 2 pi over 5. Okay? If I was doing a sine function. We're doing a cosine, but same thing. It's always going to start at 0. This number tells you where it ends. It's the length of the period. All right, let's try this one. Okay, Kristen, what's going to happen here? What's that 1/4 going to cause the graph to do? Yeah, it's going to stretch it out. Okay? In fact, it's going to stretch it out 4 times the original. Right? So if you know the period of the original, and you know it's going to stretch it out to be 4 times that amount, you should already know the new period. But we'll go through the formula and see what happens. So I've got 2 pi, which I'm going to write as a fraction. 2 pi over 1. And Gabe, what goes in the denominator? 1/4. Now, when I want to divide a fraction by a fraction, how do I do that? Do you know? Yeah. Flip the second one, which it's 1/4. It's going to become 4/1, and multiply. So what's 2 pi over 1 times 4/1? Oh, right? So you're multiplying, right? So if you multiply straight across 2 times 4, 8 pi, yeah. Which is what you would expect to happen. If your graph is going to stretch out 4 times as much, the period should become 4 times as big. And that is, 8 is 4 times as big as 2. Good. Any questions on that one? All right, so last thing we have to know before we can make a sketch is we got to figure out where the 5 points in the original table are going to move to. Okay, one column always is going to stay the same. For a period change, which column would stay the same? The y's, okay? Because you're going to stretch it left and right. So you're going to change things left and right. But you're not going to change anything up to down. Okay, so unfortunately, the y's are the easy values to work with. The 1s, the 0s, and the -1s, they're not going to change. Okay, which means we have to work with the x's. Okay, now, if you think back to our 2 original tables for sine and cosine, the first x coordinate in both is what number? 0. Now, if you take 0 and you stretch it, let's say you take 0 and you stretch 0 to be twice as big, what would it become? Double 0? Which is still what number?
0.
Still 0. And if you took 0 and you compressed it, it would be what? 0. So the first x coordinate is always 0. Because if you start at 0 and you stretch or compress the number 0, it doesn't change. All right. So now we know where we're going to start. We got to figure out where we stop. Okay? Where you stop is at the end. If I draw this in, it's at the end of one period. So you need to find out how long is one period. How do we do that? How do you find the length of the period? Gabe? That's what we just did. To find the period, use that formula. So the 5th x coordinate, okay, the last one, that's going to be given by finding the length of the period. Where do you stop? Okay. So just use your formula. And now, how many coordinates do we have all together in our table?
5.
We have 5. Right now we have 2. But what do we know about those 5 points in the table? They're not just 5 random x values. There's something special about them. They're not necessarily opposites. They're the 0, the pi over 2, the pi, the 3 pi over 2, and the 2 pi. What is special about those numbers I just said versus me saying 2, 10, 97, -8? Something special about the first list of numbers I said.
They're evenly spaced by 45 degrees.
They are all evenly spaced by how much?
45.
Well, it's 360 cut into 4 sections. 90. They're all evenly spaced by 90. So, if you know the first point and you know the last point, which point could you find, keeping in mind everything is evenly spaced? You don't have to tell me how, just tell me which one. The middle point. How could you get the middle point if you know the first one and the last one? Okay, you could add them up and then what? And divide them by 2. What is that called? Yes, it is the middle, or it's what you calculate like at the end of the term. It's your average. Okay, so to get the coordinate in the middle, the third one, all you have to do is take the first and the 5th one and average them. Okay, now once you have the middle, how could you get, say, the second one? You got to get the middle first, but then you could easily get the second one.
Take the average of those two.
Yeah, take the average of the first and the third, and then same thing to get the fourth. Take the average of the third and the fifth. By averaging things, you're finding what's exactly in the middle, and you're keeping everything equally spaced. Now, this isn't the only way to do it. There's different ways to do it, but for the kind of problems I'm going to give you, that's probably the easiest. Okay, so your second x-coordinate is the average of the first and the third. And the fourth coordinate is the average of the third and the fifth. Now, you might not always have to do all these averages out. You might start to notice a pattern. Okay? So if you start to notice a pattern in your list, you can just follow the pattern. Okay? And we'll do some that I think you'll pick up on the pattern pretty quickly. Okay, so any questions on the five steps there? So first x-coordinate is always 0. The last one is always 2 pi over your number in front of x. And then for the rest, you just average. Or look for a pattern, and you can go with that. Okay. Hey, anyone else still need to copy step D or E? Good. All right, so first thing, okay, if that was a problem on the test, you got to look at it and figure out which one of the 4 transformations it is. Phase shift, period change, vertical shift, or amplitude change. Which one is this one? Based on what we're doing today. It's a period change, yeah. Hey, but just in case we weren't sure, just so we know what it is, period change is when we multiply by a number next to x. Doesn't matter if there's parentheses, you could do that. It's still a period change. That doesn't change anything. The only thing that I could do is if I put the 2 in front like this, now that's something different. That's what we did yesterday. All right, so we know it's a period change. Wendy, when I do a period change, what column stays the same? The y's. Okay, we're going to do stuff left and right, not up and down. So Brianna, since my y's are going to stay the same, what are the original y's for sine?
0, 1, 0, negative 1, 0.
Yes. Okay, now we have to find our x's. Dave, what did I just say the first x is always, no matter what? It's always going to be 0. Okay, that's not always true with more complicated problems, but for the kind that we're doing, that will always be true. So the first x is 0. About Henley, once I get the first x value, what's the next one I have to find?
The fifth one.
The fifth one. I got to get the fifth one. And Kristen, how do I get the last or the fifth x value?
I use the formula.
Yeah, use the formula. What's in the top of the formula?
2 pi.
2 pi. And the bottom? 2. So this is going to end at pi. Okay, so we've got the first, we've got the fifth. Now we can get what's right in the middle. Becky, when I have the first and the fifth, how do I find the one that's right in the middle? Yeah, we average them. So when you're averaging with 0, that's easy to do. You just take half of the number. Right? So if you add 0 to pi, you just get pi. And what's half of pi? Just as a fraction. Got it? Yeah, Dave? Pi over 2. Okay, so that's the middle. And now you have a choice. You can do the second or the fourth. It doesn't matter. But I usually do the second one and then the fourth one. Okay, so we got to add 0 to pi over 2. How about Marcos? What's 0 plus pi over 2?
That is 2 pi.
So 0 plus pi over 2. No, not 2 pi.
I would,
What happens when you add 0 to something?
it's the same.
It stays the same. So what's 0 plus pi over 2?
I would too.
Pi over 2. Yeah. I thought you said pi over 0. We'll check the tape. So we got pi over 2. And that's what you get when you add them up. But then what do you have to do? You add them up and then take half of it. Or divide by 2, same thing. So what's half of pi over 2? Pi over 4. Okay. And if this was in degrees, I think at this point people would see a pattern. This is 0, 45, 90. The pattern is we're adding 45 each time. In radians, it's a little harder to see the pattern because you're dealing with fractions. Okay, last one. We have to average this one and that one. Okay, so we've got pi over 2 plus pi, but when we average it, we don't just add them up. What do? We add them up and then divide by 2, which is the same as just taking half of it. Same thing. Okay, why can't I add these right away? This happened when we did period change. What's that? I mean phase shift, thank you. Yes, when we did phase shift, this kind of thing happened. We had to fix these fractions so we could add them. What did we have to do? Yeah, we needed a common denominator. Okay, so Mercedes, what would be my common denominator here? 2. So if we did that, we have to multiply the bottom by 2 and multiply the top by 2. All right, so let's add those up. Devin, what's pi over 2 plus 2 pi over 2?
3 pi over 2.
Yep, 3 pi over 2. And now the last step is to take half of it, so just multiply straight across. 1 times 3 pi doesn't change anything. But what about 2 times 2? 4. And that's our last coordinate. Okay, if you had all these written with denominators of 4, you would probably see the pattern. It would be 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. But since we already reduced it, you don't see it with a common denominator, so you don't see the pattern. Okay. Any questions on the table? It's probably the hardest kind to do because you have all fractions. Okay, when you label your axes, put 1 and -1. That's going to stay the same for every problem today. What's going to change is the x's. Just label them on the lines, put the numbers in your table. 0. And if you want to label it down here, so when you sketch it, you don't draw over your labels, that's fine too. Pi over 2, 3 pi over 4, and pi. Okay, so we got 0, 0, 1, 0, -1, back to 0. All right, so compared to the original, what did this graph do? Did it stretch or did it compress? It compressed. Okay? The normal period is 2 pi. The period of this one is pi. So it compressed twice as much. Yep. Good. Any questions on that one? All right, let's look at this one. We already did one earlier in the notes with a 1/4 in front of it. Okay. So we know the y values are going to stay the same. So what are my y values for cosine? Yep. Yeah.
1, 0,
1, 0, -1, 0, 1. Okay, first x value is always 0. And earlier in the notes, when I had a 1/4 in front of x, Anybody remember what the period came out to? Yeah. Yeah, 8 pi. Okay, we did that one right here. Okay, so that's all the arithmetic for how it comes out to 8 pi. Because the period is 8 pi, it's going to be very easy to do the averages this time. We're not going to have any fractions. What's the average of 0 and 8 pi? 4 pi. And then average 0 and 4 pi again. And average 4 pi and 8 pi. 6 pi. Okay, so sometimes the numbers are a little easier to work with, like in this one. And this is when the averaging technique is the fastest. There is a better way we could have done the last one, but I'd have to show you something different. Okay, so what I'm teaching you will work for every problem, even if it's not the fastest way to do it. Right, put in your labels. 2 pi, 4 pi, 6 pi, and 8 pi. Okay, and 1 and -1. Okay, if on the test you forget to put your labels for your axes, I'm going to assume that you would go by what you always do on a graph if you don't label it, ones. 1, 2, 3, 4, 5. Right? So that would make your graph wrong. Okay, so if you don't want to go by ones, make sure you put in your labels. So technically on the y-axis here, I wouldn't mark it wrong if you didn't put the 1 and the -1, because I would assume you're going to go by ones if you don't label it. Okay? Okay, so we got 0, 1, 0, -1. I probably should have put my labels a little lower. 0, back to 1. Okay, and again, just try to make it look curved. It shouldn't look like it's a really sharp V shape. Okay, so first thing, we're multiplying by a number in front of x. If you want to know what number, it's about 1.57, but don't change it to a decimal. Okay, and because it's multiplying in front of x, that's a period change. So we're going to keep all the y's the same. Okay, Graham, my first x value, it's always what? 0. Trevor, how do I get my last x value?
It's pi over 2. Those.
It's part of what we're going to use, but that's not the last x value.
Oh, it's pi over 2 underneath.
Underneath, yep. And what in the top?
2 pi.
2 pi. And what I'm going to do is if I get a fraction in the bottom, I usually make the top a fraction as well. Okay. So last time we did this out, we just take what's in the bottom and do what? Multiply by the reciprocal. What's the reciprocal of pi over 2? 2 over pi. So what do you get when you multiply that out? 4 pi over pi. Okay, so he said there's a pi in the top and the bottom, so I can cancel it. And I just get 4. So this graph has a period of 4 radians. So it's a little bit shorter than the normal period. The normal period is 2 pi. If you want to do that out, it's about 6.28. This one is 4. So now if I do my averaging, what's the third x going to be? 2. 1? 3. Okay. So I told you this one would have the nicest coordinates of any graph all week, and it does. Those are very nice numbers to graph. So on this one, if you don't label your axes, that's okay. Because I'm going to assume you're going by ones, and that this one does go by ones. But just to be clear, I will label things so you can see it. 0, 0, 1, 1, 2, 0, 3, -1, 4, 0. And there's your graph. Okay, any questions on period change? All right, so what we'll do with the time we have left, I'll show you a couple different things with sound frequencies. The first one I'll show you is what's called an LRAD. So I don't know if you had me last year, you saw this, but does anybody know what that kind of device is used for? It's a long-range acoustic device. Dave?
It's like a riot control thing, weapon.
Yeah, it's basically a less lethal kind of weapon with sound. And the idea is that it's like a speaker, but not like the speaker I have. It's a speaker that's directional, kind of like a laser. Like a laser is very directional. You shine it in one spot, the light goes in one spot. Versus a flashlight, it's more of like it spreads out. Okay? So this is like a very focused speaker for sound. So you can aim it in a certain spot. If you're standing behind the speaker and you're the person aiming it, you don't hear it, unless it bounces off a building back at you, but you don't really hear it. The sound is just projected in front of you. So I'll show you what the device is, and they go through a couple different places they've used it in the video.
In response to the terrorist attack on the USS Cole in October of 2000, American Technology Corporation created a device like no other. LRAD, the long-range acoustic device.
A wave of the future,
A high-tech tool developed by the military.
a high-tech sonic weapon.
Long-range acoustic device, or an LRAD.
The long-range acoustic device, or LRAD, is like an audio spotlight. When you're standing alongside of it or behind it, you can carry on a normal conversation, but get directly in its beam, and the sound becomes almost painful.
Because of its weight and size, the LRAD is easy to transport, easy to set up, and mounts almost anywhere.
Cruise passengers now barely escaping that pirate attack.
We're learning more about that stunning pirate attack.
This magnificent cruise ship attacked off the coast of Africa by 21st century pirates.
The LRAD's usefulness was most recently demonstrated in November 2005 when pirates attempted to attack a cruise ship off the coast of Somalia.
It has 26 languages and about 100 different remarks, like put your hands on your head, or lie flat on the ground, or turn around and do such and such.
The system clearly enables us to enforce the Naval Vessel Protection Zone at all times.
The fact that an individual was informed of the reasonable consequences of his actions and continued to defy legitimate authority, they are personally responsible for whatever happens next.
Whether initiating communication or warding off unknown adversaries, the LRAD has proven effective more than 80% of the time and has saved countless lives in the process. From American Technology Corporation, LRAD, the long-range acoustic device.
All right, so you can see some of the examples they used in the video were like at a riot, like trying to control it. They also, I think they showed it on that cruise ship. They said 2005. I'm sure they've used it again since that. But there's actually, there was a show on TV. I don't know if it's still on, but it was called Whale Wars. Anyone ever see that show? No? Well, it was basically like a show where there were this group of people that wanted to kill whales so they could get like the oil from the whale and harvest it and make money. And then there were people that tried to stop the groups from killing the whales. And I think what happened was the people that were trying to kill the whales, they had an LRAD on their boat, a huge boat, really, really big boat. And what they would do to get the people that were trying to save the whales away from them is they would aim an LRAD right at the boats, or I think they had a helicopter too, and try to get them to go away. So I'll show you a little clip from that. You can see them kind of using it. But that's the background. There's people trying to kill the whales, and this other group of people, and the guy in the helicopter trying to save the whales.
That's it. Can't tell if that's it or not.
I was afraid it would be of a military grade because something of that caliber can actually be called permanent definite. And I knew that our small boats would be getting very, very close to these ships.
That's bad, that's bad. That's usually just absolute madness if you would use a acoustic device on someone in the helicopter as opposed to absolutely no threat to them whatsoever.
They've been attacking our crew with LRAD for a single class weapon. They're becoming really aggressive when we have to defend ourselves.
So they said in the video, it's the kind of thing that you don't want to be around it because it can cause deafness if you stand in that sound for a long enough time. And for the guy flying the helicopter, he can't really cover his ears to block the sound out because he's flying the helicopter. So the only thing he can do is move away from that sound. So that's another example of using an LRAD. So you might have, if you heard it, it's not really just like a single tone. Okay, like something like, let me turn it down a little bit. Okay, something like this. That's just a single tone. Okay, the LRAD is actually a couple different frequencies at the same time. So if I turn it down a little bit, I can let's see if I can show you a picture of what the LRAD frequency looks like. So I have it recorded. So this is an oscilloscope. Right now it's actually picking up my voice on the microphone. But if I turn the LRAD up loud enough, it'll pick up the LRAD frequency. All right, so let me turn it up a little bit. Well, maybe not that loud. Just loud enough so we can get the frequency. Okay, and let me show you picture of what I just got. Okay, so that was the picture of the LRAD. So it kind of looks like a sine wave, right? A little bit. There's definitely kind of some up and downs. It's pretty compressed because it's a higher pitch frequency. But it doesn't look like what I did when I compressed something like that. Okay, that's pretty uniform. Like the top is the same, the bottom is the same. This one, the frequency, there's some changes in there happening. And I could look at the frequency tab, and this program could actually pick out what are the individual sounds that are being made. Okay? So if it plays multiple sounds at the same time, the oscilloscope can pick out what frequencies are being played to make that LRAD sound. Because it's more complicated than just a single tone. Right? But that's a picture of what the LRAD frequency would look like. All right, so the idea of playing multiple frequencies at the same time. It has to do with, let me pull that up. It has to do with DTMF. Anyone ever heard of that? Dual tone multi-frequency signaling. Let me show you. So dual tone multi-frequency signaling, that's exactly how a phone works. Kind of an older phone that's on the wall or the cell phone you have right now. They all use dual tone multi-frequency signaling. So what that means is it's dual tone. So that's two tones played at the same time to generate a sound. So right there is the chart of the different frequencies that when you press a button on your phone, that's the sound you hear. So like if I wanted to generate the sound for a 1, okay, all I have to do is play, let's see, what is it? 697 and 1209. Okay. What I'll do first is I'll play just 697. Okay, so you can hear that. Okay, so that's 697. That doesn't really sound like a button when you press it on the phone. The other frequency is 1209. And again, if you play that one by itself, that doesn't really sound like a button you're pressing. But the key is when you play them both at the same time, it's going to sound just like you're pressing a button on the phone. Okay, so there's two tones they are played at the same time, and the way they mix together when you play them, that's that sound you hear. So what I can do with that is I can generate different frequencies. Okay? And if I call my voicemail, what I can do is it'll say things like press 4 to enter your personal options, okay, where you can change your greeting and all that kind of stuff. Well, what I'm going to do is instead of pressing a 4, I'm going to generate the frequency on the computer for a 4. But my phone will hear it, and my phone will think I pressed it. Okay? And it'll go into the options. So it does have to be kind of quiet because I'm pretty far from the speaker. It works better if you can put the phone like an inch away from the speaker, but it should still work if I do it loud enough. All right, so that should be loud enough. Okay, so I'm going to go into my voicemail. It's going to say press 4, and then it's going to say press star to exit, and we'll go from there.
Main menu. To listen to your messages, press 1. To send a message, press 2. To check receipt of a message, press 3. To change your personal options, press 4. To disconnect, press star. Personal options. To turn notification on or off, press 1. To change administrative options, press 2. For greetings or recorded name, press 3. To change notification options, press 4. To exit, press star. You have 4 saved messages. Main menu. To listen to your messages, press 1. To send a message, press 2. To check receipt of a message, press 3. To change your personal options, press 4. To disconnect, press star. Goodbye.
Right, so just by generating the right frequencies, the phone hears it and it thinks I pressed it. So that even works like when your phone is on silent, because there's 2 ways the frequency can be sent over the phone. It can hear the frequency, or you can press a button on the phone and it just sends the frequency without having to hear it. You don't have to hear it. That's why when your phone's on silent and you press buttons, you can still dial even though you're not hearing the buttons being pressed. Everything that you hear on a phone, even the ringtone, dial tone, if you get a busy signal on like a landline phone, they're all different frequencies. Okay, let's see if you recognize, this is 440 and 480 played at the same time. Okay, see if you recognize this one. Recognize that one? That's the ringing, right? When you call someone and it's ringing. That's a 440 and a 480. I don't remember all the other frequencies, but if you change that 480 just a little bit, like 490, and you play it, something sounds a little off. It doesn't sound quite right. Now, at some point, it might be okay enough that if you generated the frequency, it might work. Like if you did 485, that would be a little closer to what it's supposed to be. But things like, for example, if I played 481, and then I play 480, our ears really aren't sensitive enough to hear the difference. Right? So that kind of takes us into the last thing, which is music. So in music, a lot of times you don't generate just a single note. You play a lot of different notes together, okay, like on a guitar. And that makes a chord. So the idea is there's only so many frequencies we can hear, right? From the lowest pitch sound to the highest pitch. And even within that, there's only so many you can tell the difference between. Like I don't think anybody in here could hear the difference between 480 and 481. Maybe 480 and 484. That would be enough. You could hear the difference. So there's a video where basically a guy looks at the idea if there's only so many sounds we can hear, and there's only so many different ways you can take different notes and arrange them, will there ever be a time when we run out of music? Like we've generated every different melody you can generate, and it's all been done. And there's no other different kinds of melodies that we could actually hear because they've all been created. Has anyone ever seen that video before? All right, so we'll take a quick look at part of that video, and then he mentions something else in it, another video, and that's the last one I'll show you.
Hey, Vsauce, Michael here, and the iTunes store contains 28 million different songs. Last.fm carries 45 million songs, and the Grace Note database of artists, titles, and labels contains 130 million different songs. That's a lot. If you were to listen to all of the songs in the Grace Note database, one after the other, and a giant playlist, it would take you more than 1,200 years to complete. But since there are a finite number of tones our ears can distinguish, and because it only takes a few notes in common for two musical ideas to sound similar, will we ever run out of new music? Will there ever be a day where every possible brief little melody has been written and recorded and we are left with nothing new to make? A good rule of thumb might be to say that if modern recording technology can't distinguish the difference between two songs, well, neither could we. So let's begin there, with digital downloads, MP3s, CDs, and a calculation made by covered in Bs. Digital music is made out of bits. Lots and lots of bits. But each individual bit exists in one of two states, a 0 or a 1. Now what this means is that for any given, say, 5-minute long audio file, the number of possibilities, mathematically speaking, is enormous, but mind-blowingly finite. A compact disc, which samples music at 44.1 kilohertz, is going to need about 211 million bits to store one 5-minute song. And because a bit can exist in two states, either a 0 or a 1, the number of possible different ways to arrange those 211 million bits is 2 to the 211 millionth power. That value represents every single possible different 5-minute long audio file. But how big is that number? Well, let's put this in perspective. A single drop of water contains 6 sextillion atoms. 6 sextillion is 22 digits long. It's a long number, but the total number of atoms that make up the entire Earth is a number that is about 50 digits long. And estimations of the total number of hydrogen atoms in our universe is a number that is 80 digits long. But 2 to the 211 millionth power, the number of possible different 5-minute audio files, is a number that is 63 million digits long. It is a number larger than we can even pretend to understand. It contains every possible CD-quality 5-minute audio file. Inside that amount is everything from Beethoven's Fifth to Beck's Loser. It even contains a 5-minute conversation you had with your parents when you were 3 years old. In fact, every one of them. It even contains every possible conversation you didn't have with your parents when you were 3 years old. But it is finite, not infinite. It's cool to think about, but it doesn't come very close to answering the question of this video, which is how many possible different songs can we create and hear the difference between. So for that, we're going to need to narrow down our hunt. On everything 2, Ferris Lepidoptera made a calculation that involved some assumptions that I think helped narrow the field down in a really nice way. She took a look at the total number of possible different melodies you could create within one octave, containing any or all of the intervals we divide octaves into. Of course, sound frequencies can be divided much more granularly than that, but giving ourselves more notes might mean we could make more technically different melodies, but they wouldn't necessarily sound any different to our ears. Now, given a single measure containing any combination of whole, half, quarter, eighth, 16th, or 32nd notes, she calculated that there would be this many possible unique measures, which is a smaller number than we had before, but to put it in perspective, this is how many seconds old the universe is. Uric DE's calculation is even more specific. He stayed within one octave, but instead of looking at a complete measure, he only considered the number of unique combinations of 8 notes. He also assumed that typical melodies, as we know them today, only contain about 3 different types of note length. For instance, quarter, eighth, and 16th, or whole, half, and quarter. To be sure, that will most likely not always be true. Musical tastes hundreds, thousands of years from now will most assuredly be different. But given melodies as we know them today, across 8 notes, over 12 intervals, there are about 79 billion possible combinations. We're getting relatively small here. I mean, under this definition of melody, 100 songwriters creating a brand new 8-note melody every second would exhaust every possible melody within only 248 years. But it's still a huge number, way bigger than the total number of songs that have been written that we know about. So you can quite safely say that, no, we will never run out of new music. But here's the rub. If that's the case, why are there so many commonalities between songs, even across hundreds of years? How come so many songs kind of sound the same?
And then he mentions a video you can look at that shows different songs sounding the same, so that's what we will finish up with. Okay. While we're finishing that up, I'll pass out the homework for tonight.